Swayam Prabha. Digital India. Educated India.
So from these sets of equation, let us try to evaluate the parameters. Suppose starting from these equations, let us start with this one. Let's say S13 magnitude is equal to 0. Then substituting this value in this equation will give S12 magnitude equal to 1. Okay, so now because then this means this is not equal to 0. So then if we come to this equation, since S12 magnitude is not equal to 0, so then S32 magnitude has to be equal to 0. And then if we substitute this value in this equation, then we get S31 magnitude is equal to 1, which again is not equal to 0. So if S31 magnitude is not equal to 0, then from this equation we have S21 magnitude must be equal to 0. So our S parameter matrix was this. Now from these sets of equations we have our matrix is like this: 0, 0, 0. Okay. Now S12 is equal to 1, 1. S31 is equal to 1. Okay, these two are 0 also. And from S21 equal to magnitude equal to 0, we also get S23 magnitude equal to 1. So these are 1. This is also 1. Now here one thing that I have not shown is that since we don't know the phase, we cannot write it strictly speaking like this. There will be a phase term here. For example, this might be some theta 1, this might be theta 2, this might be theta 3, like this. J, J. Like this. So again, by adjusting the lengths of the various ports, we can eliminate these phase terms so that we will be left with only the amplitude terms. Okay, so in this case, for example, it will be like this. All other terms will be 0. So this is one solution. Had we started, for example, now here we started with S13 equal to 0, but we could have started with, for example, S23 magnitude equal to 0, in that case we would get a different in that case the S parameter matrix that we would get would be something like this. Okay, so there are two solutions for the circulator, and depending on how we design our circulator, we can have two different types of S matrix. One is this one, the other is this one. So the symbol of a circulator, excuse me, is given like this. So if signal is flowing in this direction, then the S parameter matrix which will be applicable is, so if signal is flowing in this direction, it means that signal cannot flow, say, from port 1 to 3, so then S31 should be equal to 0. So S31 is 0 for this case. So let me redraw this. This is port 1, port 2, port 3, and the direction will be like this. So S31 should be non-zero. Therefore, this particular configuration is represented by this this matrix. Okay. So in this case, S31 is non-zero because signal is flowing from 1 to 3. So S31 cannot be 0. That's why this is the S parameter matrix. Whereas in this case, signal is flowing from 1 to 2. Hence S21 cannot be 0, which is the case for this matrix. And S31 has to be necessarily 0, which is again the case here. In this case, S21 has to be 0 because signal is not flowing from port 1 to 2, and that is what we see here. S21 is 0. So now the question is, how does it happen? How do we achieve this non-reciprocal nature? The way it happens is because of the presence of certain types of materials called ferrimagnetic materials. Now, I won't go into the details of what are ferrimagnetic materials. Just that, say we have a circular slab of that material, there is always an inherent magnetic field present. Now, because of the presence of this magnetic field, currents that are flowing in this direction will be producing a different magnetic field as compared to a current flowing in this direction. A current that is flowing like this will add to the magnetic field present, whereas a current flowing like this will subtract from the magnetic field present. In general, it can be shown that for these materials, when you introduce a signal here, there are two waves being propagated. One in this direction, let me use this, one in this direction and the other in this direction. And depending on the constructive and destructive interference of these two waves, we actually get the electric field distribution over the entire 360 degree, something like this. Because of the distribution of the electric field, as you can see, suppose this angle is say 0 degree, then say this is 120 degree, and say this is 240 degree. You see, if the signal is inputted at 0 degree, then at 120 degree the signal value will be the same as the input, but at 240 degree there will be 0. So this is how the circulator is obtained. Now, what are the uses of circulators? A circulator can be used for a variety of circuits. I'll just, yes, it's visible now. So these are some of the applications of a circulator. The first is an amplifier. So in an amplifier at port 3, so the circulator has a sense like this, that power flows from 1 to 3 and then to 2. This is port 3. At port 3, I connect a negative resistance. So any signal that goes from port 1 to port 3 after reflection at port 3 will be amplified, and this amplified version of the signal will be sent to port 2. So but then no signal will come back from port 2 to port 1. That's why the signal flow is in a single direction, and that's how this amplification action is achieved. One other use of circulators is to, here as we see, so in this circulator power flows from port 1 to 2 and then to 3. This is port 3. Port 3 is terminated with a matched load. So any signal traveling from port 1 to 2, at port 2 there might be some reflection which will be transmitted to port 3, but then since port 3 is matched, there won't be any further reflections from port 3, and so there will be no signal coming back from port 2 to port 1. So that's how an isolator action is achieved, that power can flow only from port 1 to port 2. Any signal reflected at port 2 will be absorbed at port 3, and port 2 will not, and direct transmission from port 2 to port 1 cannot happen. Now in this case, in the case of the amplifier, of course, there can be transmission from port 2 to port 1 after reflection. Yes, that is possible. So that's the difference between this amplifier and isolator. In isolator, there is zero transmission from port 2 to port 1, but in amplifier, port 3 is used only for amplification, but there can be reflected waves from port 2 to port 1. And then finally, one other use of circulator is what is known as a shared antenna. So for transceiver systems, we often need to use the same antenna for transmission and reception. One way to do that is either have what is known as FDD, that is frequency division domain duplexing or time domain duplexing. But that requires a lot of time and frequency resources. We have to have double the number of channels that are actually used. One set of channels for the transmitter and one set of channels for the receiver. Instead of that, this is a system that could be used where the antenna, any signal received by the antenna, is sent to the receiver along one path, and the transmitter will send signal to the antenna through a different path. The two paths do not match, and therefore there is no chance of mixing. So these are some applications of a circulator. So with that, we come to an end to this part on, that is, circulators. In the next part, we'll be covering power dividers. Hello, welcome to the final part of lecture 12. In this part, we'll be covering the third type of three-port network, which are called power dividers. So we have already covered the first type, which is the T's, the second type, which is the circulators, and the third type is the power divider. So let me share my screen. So as I had mentioned in the previous part, that power dividers power dividers have two important properties. One is they are reciprocal, and the second one is matched at all ports and lossy. So they are not lossless. So in a three-port network, therefore, a power divider will take power. Suppose this is our power divider. If this is a three-port device, there is say a port 2, port 3, and a port 1. Power will be inputted at port 1 and outputted at port 2 and port 3. Okay. Now, ideally, there should also be what is known as isolation between these two ports. So any power entering or exiting from port 2, say, should not affect the power entering or exiting from port 3. In other words, S23 or S32 should ideally be equal to 0. This is the condition of, this condition is known as isolation. Okay, so let us start with a basic resistive power divider. So resistive power divider is like this. Say if Z0 is our characteristic impedance at all the ports, this is my port 1, say this is my port 3, and this is port 2, and I can further the other terminal of the transmission line. So now from this circuit, it should be clear that all the ports are matched to Z0, and all the input impedance at all the ports when a matched load is connected at the other two ports is Z0. This we can show simply, suppose let us consider port 1, and since this circuit is symmetric across all ports, the results obtained for one port will be the same for the other two. Okay, now suppose port 3 is terminated by Z0. So this is port 3, this is port 1, and this is port 2. And also say port 2 is terminated by a matched load, and say if you are trying to find out what is Z in here. So Z in is nothing but okay. So this shows that Z in at all ports when the other two ports are terminated by a matched load is equal to Z0, and so this implies then that gamma in equal to 0. So now suppose you have a power P in flowing at port 1. The power that will be flowing to port 2 and port 3 from symmetry, we can say that is, it will be P in by 2 here and P in by 2 here. So from here we can directly say that S31, S32 or S21 will be equal to half, right? Similarly, S S12 will be equal to S13 will be equal to half, and S23 will be equal to S32 will also be equal to half. So from here we can write down the S parameter matrix for this resistive power divider as, first of all, it's matched at all three ports, and all the other terms are simply 1. So this is the S parameter matrix. One problem with this resistive power divider is that it doesn't provide isolation between the output ports. So power, any change in the circuitry at this port will affect the power flowing out at this port. This is one disadvantage of this resistive power divider. So in order to correct for this problem, we have what is known as a Wilkinson's power divider. A small correction here before we move to the Wilkinson's power divider. The correct S parameter matrix for a resistive power divider should be as like this. So first of all, the diagonal terms are 0. So this half term was missing. Please note this. So in a Wilkinson's power divider, first of all, the circuit is not as symmetric as in a resistive divider. So there are designated input and output ports, whereas for a resistive power divider, there are no designated input and output ports. All the ports are identical and symmetric. But here in a Wilkinson power divider, the power has to be inputted at a specific port and outputted at specific ports. The circuit diagram is like this. Now, to understand this circuit, first of all, if we calculate the input impedance here, so to calculate this input impedance, we see that this particular component of the circuit is not necessary. This doesn't, because of the symmetry along this line, what happens is this 2Z0 doesn't play any role. So we can simply reduce the circuit like this. So this is okay. So the input impedance seen here is square 2Z0 whole square upon Z0. So this is equal to 2 of Z0, and that is the same value seen here. So the overall Zin seen here is half of this quantity. So Zin is equal to Z0. Now to see the input impedances from the output ports, at the output ports, we do what is known as an odd even analysis. So the odd even analysis involves, let me redraw that circuit for Wilkinson power divider. So in this equivalent circuit, let us suppose that we have connected an input voltage like this, value Vg. Now this voltage source can be considered as equivalent to two, as the superposition of two different cases. In the first case, we have a source Vg by 2, Vg by 2 here, and this point is also connected by Vg by 2, and in the second case it's like a So what I'm trying to say here is that this source VG connected between ports 2 and 3, this is port 1, can be resolved as the summation of two different circuits. So this circuit where the inputs to port 2 and 3 are the same is called the even mode circuit. And this one where the inputs are equal and opposite to ports 2 and 3 is called the odd mode. Now, when the inputs to port 2 and 3 are equal and of the same sign, then what happens is this line of symmetry, this one, along this line of symmetry, the potential or this line of symmetry can be considered to be open. It's as if, think of it this way, that this circuit is symmetric about this line, and I am applying equal and same voltages at ports 2 and 3. So these Z0s are basically open at this point. And this line, red line, represents a open line, as if everything connected along this line is open. On the other hand, for the odd mode circuit, where the inputs are equal and opposite, this line of symmetry represents a short. It's a short because the potential will be, whatever be the potential at this point, it will be equal and opposite to the potential at this point. So, and since these two elements are the same, so this point should always be at, this point should always be at zero potential. So with this in mind, I can have the half circuits for the even and odd mode. So for the half circuit for the even mode will be something like this. Now here, suppose this port 1 is terminated by Z0, then I can consider Z0 to be a combination of two shunt impedances. So here for the, so when this for the even mode circuit, actually I should connect it like this. So for the even mode circuit, it's like this. So the input impedance that I calculate here, this is the, so see, this Z0 doesn't play any role in the calculation of Zin, and the input impedance at this point is basically 2 square root of 2Z0 whole square upon 2Z0, which is equal to Z0. The odd mode half circuit will be, so for the odd mode, recall that this point is a short, so these two impedances don't come into the picture because this is the short. So for the odd mode, the equivalent circuit is similarly this point is also short. Now since this point is shorted, so the input impedance here will be infinite because this is a quarter wave transformer. So input impedance infinite means this point is basically open, and the Zin will nothing but this Z0 because from this point onwards it's open. So Zin is equal to Z0. So we see that for both the odd and even modes, the input impedances at port 2 and port 3 will be Z0. And so all the ports are matched. And also from this odd and even analysis, you see that either the line of along the line of symmetry it's open as in the even mode, or it is shorted as in the odd mode. So in both cases imply that any signal, spurious signal in port 2 will not appear at port 3 because either along the line of symmetry it is open or it is shorted. Hence port 2 and 3 are isolated from each other, which was not the case for the resistive divider. So now coming to the S parameter matrix, what will be the S parameter matrix? So we can again, have a qualitatively we can find out. First of all, you see that all the ports are matched, so the diagonal elements will be 0. Okay, then we have port 2 and 3 isolated, so S23 and S32 will be 0, and S12, what will be S12? Now just by looking you can see that since the power is equally divided between, that is power entering port uh, power entering port 1 is equally divided between ports 2 and 3. So S12 magnitude will be 1 upon square root of 2. Similarly, S13 magnitude will be 1 upon square root of 2. But what about the phase of these two S parameters? That we can understand again qualitatively by looking at the phase shift produced by these quarter wave transformers, and being a 90-degree electrical angle, the phase of S12 will be minus J, or I should say it is minus pi by 2. Similarly, phase of S13 is equal to minus pi by 2. Okay. So with these in mind, I can write the S12 parameter as nothing but minus j upon square root of 2 1 3 as minus j upon square root of 2. So overall the S parameter matrix becomes minus j upon square root of 2 minus j upon square root of 2 j upon square root of 2 minus j upon square root of 2. So this is nothing but minus j upon square root of 2 0 1 1 1 0 0 1 0. So this is the S parameter matrix of the Wilkinson power divider. Now we can also have now the layout of the Wilkinson power divider. So let me, yes. So the layout of the, so this is the circuit, this one. The layout is something like this yellow diagram. So here this rounded shape and this rounded shape represent this lambda by 4 and this lambda by 4 sections. We can also have a broadband version of this Wilkinson power divider where instead of one rounded oval section, we have a number of oval sections, each catering to a particular frequency. So Pozar shows one example of how to design for multi-section Wilkinson power dividers. So with that, also to lecture 12. In the next lecture, that is lecture 13, we'll be starting with couplers, which are 4-port microwave devices. Thank you.